Fantastic. Yes, go ahead. Sorry.
Good, good, excellent. Okay, so I can share again. And all right, oops.
Okay, is all ready now?
Yes.
Okay. Can
Yes.
everyone see the slides?
Yes.
Yes,
And,
maybe. Okay, yeah, yeah.
And do you see the cursor if I move like that?
Yes.
Okay, so I can, okay.
Mm.
All right, so I should get started.
Okay, the next speaker is Professor Abdelmalek Abdesselam, and he will talk about rigorous nonperturbative results related to p-Adic antidecedent conformal field theory. Please.
Thank you, Branko. Well, first, thank you to the organizers for organizing this conference, even in these difficult times. And thank you for the opportunity to give this talk. Here is the plan of my lectures. First, some general introduction. Then the second part called the hierarchical continuum. I'll explain how you move from quantum field theory over the reals to p-Adics. And finally, the third part is about the main conceptual innovation by myself and my coworkers, which is a rigorous way of doing renormalization group with space-dependent couplings, and this is the key to our results. All right, I'm not assuming that people, can you see the top? Oh, maybe my slides are a bit too, okay. So I will start first by explaining very quickly what quantum field theory is about, since I don't know if everyone here is familiar. So a quantum field theory model on RD, so d-dimensional spacetime. There's, of course, lots of ways to define this, but one way to do this is to say that it's basically a collection of so-called correlation functions indexed by n, the number of points. So x1, xn are n points in RD, and we look at a function of these n variables. And they are, if you look at the physics textbooks, they're given by this kind of formula here. So what does that mean? This is an integral over omega. Omega is a space of functions from RD into R. So this is just for the example of a scalar field. So what do we integrate? Well, we have here d phi. This is the Lebesgue measure on this space of functions multiplied by a weight, which is exponential minus a certain energy, which is obtained by integrating over space, say the square, the fourth power. We've seen something similar in Wilson's talk. And also this is the kinetic part, which is the integral of the gradient squared of the field. Phi is called the field, is actually the integration variable. Z here is a normalization constant. So it's basically the same integral, but without these evaluations of the field at these fixed points x1, xn. And so formally, this whole thing, okay, it doesn't really make sense for a mathematician, but at least it looks like the moments of a probability measure. So the probability measure is basically d phi times this weight times the 1 over z normalization factor. So it's a probability measure on a space of functions, omega, the probability space here. And one is particularly interested in conformal field theory, CFTs. So that's the case where these correlations satisfy conformal invariance. All right. I don't know if you can see the. Can you see the very top of the slide, or it's maybe I should leave the full screen. No?
Yes. Yes.
Is it better? Oops. Maybe I'll do this. Okay, because the top seems to disappear. Okay, so from a mathematical point of view, what I just wrote is doesn't make sense. And we know why. First, there is no Lebesgue measure d phi because omega is infinite dimensional. And so in order to make sense of this, what one can do is to discretize, replace the continuum by a lattice, and also not just an infinite lattice, but make it into a finite grid That means you also work in finite volume, and then you try to take weak limits of well-defined probability measures. So the way I'm going to do this to fix some notation is pick some number L. L is just a way of organizing scales. So we're going to use powers of this fixed number L to organize scales from very small to very large. L could be 2, for example. I'm going to introduce 2 length scales, L to the R. R is a very negative integer, so that's going to define the mesh of the lattice. So I replace RD by this lattice, and also I put everything into a box of linear size L to the S. S is another integer, which is going to be very positive. So this replaces the domain of my fields, so the space of the fields omega, by a finite dimensional space, which is basically R to the total number of points in the grid, which is exactly this quantity here, the ratio of scales at the power d. And now the goal is to obtain the probability measure, I will call it nu, whose moments are these correlation functions. I'll try to obtain it as a weak limit of probability measures, which depend on these 2 parameters, R and S. So R is going to go to -infinity and S to +infinity. And so this is also similar in spirit to how people in Monte Carlo numerical techniques, they compute these integrals. So here is an example that I took from this paper by Talapov and co-workers from a team from the Landau Institute from 1993. So they were looking at a conformal field theory. So in that case, so this is for the 2-point function. So it's the case where there is only 2 points, and little n is equal to 2. For a conformal field theory, the 2-point function is given by 1 over a certain power of the distance between the 2 points. It has a very simple form. And so in this model, they actually know the value of this correlation, but it's by exact computations. And so what is plotted here is the simulated 2-point function divided by the exact power law corresponding to the CFT. But I wanted to show this picture because it tells you when you do this discretization, where do you see the conformal field theory? And here it's in the middle, right here. This is where the ratio of what the numerics tell you and the exact result is pretty much equal to 1. Now, so on the horizontal axis, this is basically the distance between the 2 points. And here is the evaluation of the correlation, or rather divided by the exact continuum limit. And here they say they have 1024. This is for a 2-dimensional model. So this is actually, the grid has more than 1 million points, which is extremely impressive since this is 1993 computers. Anyhow, so you see on this picture that in the intermediate regime, this is where you have what we really want to understand, the conformal field theory behavior. If you look at a distance between the 2 points, which is too small, this is this part here, then you start seeing some junk, this part here, deviations. That's because you are seeing the scale, you're too close to the scale of the lattice, so you see the results are contaminated by the lattice artifact. On the other hand, if you go to the other extreme here, so this is when the distance between the 2 points is very big, it starts also becoming junk. I mean, this is garbage. It's because you are getting too close to the size of the box. Okay, so really what we want to understand is the part in the middle. I was looking for this kind of reference for a long time and was unsuccessful with Google search, etc. But I have Slava Rishkov to thank for letting me know about this reference, which has this nice curve. Anyhow, let me now talk about AdS CFT. I mean, it's a touristic, impressionistic review, very quick. So what's going on? So we start from RD and we add a point at infinity. So we obtain a compactification, which is just a d-dimensional sphere. And so there is a group which acts here. It's the Mobius group, or the group of global conformal transformations. So this is the group of bijective transformations of this compactified RD. generated by the isometries of RD, dilations, and you need to throw in a transformation like the inversion, the unit sphere inversion. So an alternate definition of this group is the invariance group of the absolute cross ratio. So the x1, x2, x3, x4 are points in RD. So you look all bijections which preserve this. That's another way of defining the Mobius group. In the so-called conformal ball model, so this is like the Poincaré disk, this compactified space-time RD plus points can be seen as the boundary of a d+1 dimensional ball, which is equipped with this hyperbolic metric. Another model for the geometry of what's going on is the half space model. So in that case, we see RD as the boundary of RD times another direction, 0, infinity. So this is called the denoted by Z in the physics literature for the coordinate in this direction. So this is mathematically just the d+1 hyperbolic space with this metric. So this is the d plus first coordinate. And a remarkable fact from geometry is that there is a one-to-one correspondence between elements of this conformal group, the Mobius group, and isometries of this extended space, either the ball or the half space. This is like for d = 1, this would be the Poincaré upper half space, or Lobachevsky. So this space is also called the Euclidean AdS space in the physics literature. And so there is this remarkable one-to-one correspondence between conformal maps on the boundary and isometries of the bulk or interior. So when looking at the conformal field theory on this boundary, RD, so you have a bunch of fields, before I call it phi, but let's call it O here. And we look at correlations, and they satisfy a invariance property, which is when you move the points by one of these conformal transformations F, there is a relation between the correlations, which involves, so this is just the Jacobian. So at the power 1/d, this is like a local scaling factor, a dilation factor. And delta here is something which is characteristic of the field called the scaling dimension. All right, so there is this AdS CFT correspondence discovered by Maldacena and lots of people, which postulates a relation between conformal field theory on the boundary, which is RD, and more sophisticated field theories or string theories in the bulk. And so one way, this is a simplified version in a certain limit, semi-classical limit, but one way to try to make this a bit more precise is that if you, this is kind of what Wilson was talking about, a generating function of correlations for the CFT involving a source term J. Well, it is possible in principle, if one believes this correspondence, to compute this generating function as, so this is a classical approximation, but exponential minus a certain action for a field which lives on the bulk, so it has d+1 coordinates. Phi x is a particular, so this is, it's an extremal field configuration, which essentially makes the action extremal when you impose a certain boundary condition, and this is where the relation to the source is. We want the field to asymptotically near the boundary behave like this. Okay, so there is a relation. All right, so now the problem is that we don't really know what this thing is. I mean, people have been trying different, so this holographic correspondence, the problem is that this action S of phi is mysterious for the bulk. But physicists have been working with models which kind of look like this. So G is the invariant metric, the hyperbolic metric. All right, so you start by putting some phi squared, and you can put higher order terms. The mass is here not allowed to be too negative. There is a certain bound. that needs to be satisfied. But the remarkable fact is that when you compute perturbative expansions, so the analog of Feynman diagrams for this kind of theory, they're called Witten diagrams. And when you compute, one of the simplest is a diagram which looks like the Mercedes logo. So it has 3 points on the boundary, 1 point in the bulk integrated over, and it forms basically a star with 3 branches. And so when you compute this Witten diagram as a function of the locations of the points in the bulk, you find exactly this formula, which is well known to be what is expected from conformal field theory. All right, so the good news is that almost everything I said can be, I mean, there's an analog, there's a dictionary, you can make sense of it in the hierarchical model, or I mean, or over the p-Adics. So there's been work by Melzer, Lerner, and Nisarov defining precisely what does it mean to be a conformal field theory over the p-Adics. And more recently, there's been work by Gubser and co-workers to define this AdS CFT correspondence in this situation. So the main result I'm going to talk about is this paper from 2013 with my former student AJ Chandra, who is now at Imperial College, and my colleague at Virginia, Gianluca Guadagni. And there we basically construct one of these, so n here is the number of components, we just take n equal 1, so a scalar field. So we rigorously construct this, I mean, we didn't prove it's a CFT, but we removed all the cutoffs. So we constructed the field phi, but most importantly, that's really the new result, is we constructed the square and also obtained results about the scaling dimensions, and this, which were also predicted by Gubser et al., but we proved this rigorously in our paper. All right, so this is for the introduction. Now let me move on to the model. I need to remind you of some notation. So here P is a prime number. What I'm going to do is I'm going to replace RD by QP to the D. So now the space of functions is going to be a space of functions from QPD into R. So the distance, so for a point in QP to the D, I'm just take the maximum of the p-Adic absolute values of components and use this as my norm if you want to measure distances. For each k, I will look at balls, closed balls of radius pk. Another way is to think of this quotient of this as cosets. And so L to the k, this corresponds to, okay, so balls of a certain radius. And as we know, because of the ultrametric property, when you look at all the possible k's, these form a tree. So here is the picture. So this is for p equal 2 and d equal 1. If we take, for example, the origin to correspond to the branch going all the way to the left, then this point here, this is zp to the d, okay, right here. So at this level, basically you have all balls of radius 1. Then you have the smaller ones here. So this is just to give you, to keep in mind the labeling. And of course, QP to the D is basically the set of leaves at infinity of this tree, which I call the hierarchical continuum. So QP to the D is the set of leaves at infinity. Whereas the tree itself, as an infinite graph, this is going to play the role of the hyperbolic space because, well, it's a graph, so it has a graph distance, which is just how many edges between 2 points. And using this picture, a point in QP to the D is the same as a path along this tree coming from all the way down at my below at infinity. All right. So as we know, p-Adic numbers have an expansion like this, which of course truncates if you go too far in the negative powers. So here we have D components. So we have, for each power of p, we have d digits. So I package them like this. And so these kind of give me a way of choosing the next small box or cube inside the bigger cube. So this is just another way of visualizing p-adic, tuples of p-adic numbers. Just to remind you how you rescale, when you multiply by p, you know that things become smaller. So in the picture, that means that taking a path and actually shifting it up by 1 unit. Likewise, if you divide by p. The distance, so this is perhaps more important. So you have 2 points in qp to the d at the boundary at infinity. How can you see what the distance is using the tree? It's very easy. The two paths at some point, if you go down, they have to merge. So they merge at a certain layer Lk. And well, then by decree, you can say that the distance is p to the k. Okay, and of course, keep in mind that when you multiply inside by p, you become smaller by a factor of p. So hold on. So again, just so you see here, this is how things are numbered. So for example, here, if you have a point going here and then a point going over there, then the distance is p to the -2. Okay, all right. And also the nodes of the tree, the vertices of the tree are in one-to-one correspondence with these balls, because if you look at the node, you can look at all the paths which go through that node and then go somewhere at the boundary, qp to the d, which form a kind of cone if you want. And so the endpoints here, this is precisely the points in the ball. Finally, remind you that there is a Lebesgue measure, the additive Haar measure, which I will just denote by ddx, which gives volume p to the d times k to balls of radius p to the k. So one could argue that this whole thing is really one dimensional. So where is the dimension here? It is right here in the dependence between the volume and between volume and distance. Finally, there is a particular role given to the unit lattice, which would correspond to L0. So basically ZP to the D and all the cosets of the quotient. And we can also define a distance between this discrete set of points by just picking the smallest p-adic distance between a point in this box and a point in this box. Okay. Now I'm going to define a Gaussian measure to be perturbed. So I'm going to give you a different definition from what Wilson gave you in terms of Fourier cutoffs. Hopefully this is going to be a bit more intuitive. So what's going on? I'm going to put some random variable. So zeta sub x, x corresponds to a node somewhere in the tree. So everywhere in the tree, I'm going to put some Gaussian, say n01s. But I'm going to put some dependencies in the following way. Whenever I see a point in the tree, of course, there is the offsprings. Okay, the G is the set of offsprings. So there is a P to the D offsprings. What I'm going to do is I'm going to condition and impose by force that all of these offsprings, they add up, the random variables add up to 1. Okay, so you start from independent n01s and you condition on the sum in each group, in each family like that, have to be 0. Okay, so it's equal to 0 almost surely in every group. But then from this group of offsprings to the one next to it, it's completely independent. Okay, so what we have is a collection of random variables, zeta x. This is boldface x, I don't know if you can see, indexed by points in the tree. Now we also can define clearly a notion of ancestor. So if we have a point in the tree at layer k, and we take k prime, which is bigger, so that means lower, then there is a unique ancestor at scale k prime, so in the layer k prime. Maybe I should go back to this picture, you see. If you take a point here, the k is -2. There is a unique ancestor here at k prime equal 1. Okay. All right, so there is a notion of ancestor. And so now I'm going to define a field which lives at the boundary. So qp to the d. and it has what is called the scaling dimension. So this time I'm not using delta like physicists do, but this symbol here. So it's just a parameter that I can pick any way I want. So here is the definition. So X, remember, is a point in the boundary. So what I do is I collect all the random variables which live on the ancestors of that point, and I multiply them by this geometric weight, and I sum. And so this way I have a function which depends on X. Okay, so so if you have a point here, basically you look at all the sites in the tree corresponding to the path, you collect the zetas, the Gaussian variables which live along there, and you sum them with these geometric weights. Now, as you can see, this is a geometric series, which is, so the phi here is actually positive. So this thing here becomes really big when k is very negative. So when you go towards the boundary, so there is a blow up. In particular, formally, if you compute the 2-point function, the covariance of this random field phi, what you find is this. Okay, so this is like the Green's function I was asking Wilson about. In my situation, this blows up at x equal y. And the way it blows up depends on what I pick for this scaling dimension. So in my situation, if I want a space where I can define a probability measure with this covariance, it has to be a space of distributions, not test functions or functions. Okay, so here I should put the p-adic, the p for the p-adic distance, but okay, from now on, I'm not gonna, everyone knows what the p-adic distance is here. Okay, so just to remind you, test functions. So I will say that a function is smooth if it's locally constant. We have the Schwarz-Brouwer space of compactly supported smooth functions. We define a topology there, which is a locally convex topology generated by all possible semi-norms. So this is also called the finest locally convex topology. Now to define distributions, so I have to take the dual. And I put on it, okay, I like to put strong topology, but here it happens to be the same as weak star. If you want to see what this space of test function is from a functional analytic point of view, so this is isomorphic as a topological vector space to just a direct sum of R. So kind of like what Wilson was saying, that it's a union, a countable union of finite dimensional spaces. When you take the dual, so the space of distributions, this is in fact isomorphic as a topological space to R to the n, the space of sequences of real numbers. And the nice thing, so I'm going to take my omega probability space to be this space of distributions. And if you think of it as R to the n, countable product of Polish spaces is Polish. So this is a very nice space to do probability theory on. Okay, now the model, the precise model we worked on, so which I call the p-adic CFT toy model. So the goal is to understand eventually conformal field theories over R in 3D, but this is very hard. I'm going to set D equal 3 in the p-adic case. The choice of scaling dimension is exactly 3 minus epsilon over 4, where epsilon is a small positive number. You'll see later why. This is basically being close to mean field, but non-mean field. So this is, if I put epsilon equal 1, this would be basically trying to understand the three-dimensional easing model, but that's too hard. So I need epsilon small to be close to the mean field situation. Now for the L, the number I use to go from one scale to another, I will use T, the prime number, at some power little l, which is fixed. So this is, so used to go from one scale to the next. Once again, R is going to serve as UV cutoff. So that means that the smallest scale in the system in X space is L to the R. It's going to go to 0. The infrared cutoff, that's the size of the box. That's going to be L to the S. Now, the Gaussian measure I'm going to use is, so before we had something which, I mean, looked simple formally with this covariance, but the problem is that I have something which diverges. So that means I cannot really evaluate my field pointwise, but I can define local averages. So it's a distribution. So what I'm going to do is I'm going to stop. I'm not going to go all the way to the boundary. I'm going to stop at a certain k, which is r times little l. So if r goes to infinity, then I have the whole range of scales, but I'm going to stop before I reach the boundary or the leaves of the tree. So when you do this, you have a very well, I mean, this is a random field which is made of locally constant functions, which are locally constant at scale L to the R. They're not compactly supported, but they're nice functions. Moreover, there is a nice action of scaling by powers of L, which relate these probability measures to each other. So the mu C0, so this is like putting a cutoff at unit scale. If you take a field sampled with that probability measure and you want to make a field sampled with the mu CR covariance, all you have to do is take this. So these are scaled copies of each other. So just to relate to Fourier description, you can also define these measures using Fourier. This is the non-cutoff measure, which is really living on distributions. So the propagator in Fourier space is 1 over xi to this power. So here phi is positive, so this is less than d, and so it's not integrable at large momentum. And that's why this thing blows up when x1 is close to x2. This is the fractional part, the usual formula for Fourier in p-Adic setting. And this is the cutoff version, which gives you nice sample fields, nice functions, which are locally constant. So here I just put a sharp cutoff function, an indicator, which kills momenta, which are larger than L to the minus R. R is going to go to minus infinity, so this is going to become bigger and bigger in momentum space. Now, fix what are called dimensionless parameters, G and mu. And you can, I'm going to define scale dependent. So this is where renormalization enters in. So the coupling constant is a function of R, which is the UV cutoff with precisely this dependence. So this is actually going to, this is going to plus infinity. And same thing for this mu. So this is not the Gaussian measure. This is just a coupling constant. Sorry for the using mu for two different things. This also corresponds to the scaling you get if you start from a unit lattice, say like critical easing model, and you try to get the conformal field theory by just rescaling that critical lattice model. You get similar dependence. So I use notation lambda s for the ball at the origin of linear size L to the S. So that's my volume cutoff. I'm going to integrate. So these are Hermite polynomials. So you can forget about that. It's just the fourth power of the field, the second power with these coupling constants over not the whole space QP to the D, but this box. And so now this is this gives you a well-defined probability measure. You start from the cutoff Gaussian measure, you multiply with this, and everything makes fine. Z is a normalization constant. So phi sub RS, this is going to be a random distribution on S prime of QP3, which is basically sampled according to this measure, probability measure mu RS. I'm going to actually introduce also a squared field, which I will denote following Zimmerman like this. And so, all right, it has a complicated formula here, but so this is in principle a distribution. So if I integrate it against J, which is a test function, how do I do this? Okay, I start from the this is basically phi, the square of the field phi RS minus an additive constant. And here's this is the one you do for the Gaussian measure. And here is another additive correction. Finally, in front here, there is a multiplicative renormalization, and this is highly non-trivial. Z2, Y0, Y2, these are just constants, which will need to be adjusted in a sec. And there is also a constant I'm going to use to multiply my original field. But what I'm going to do is to look now at the pair of random distributions, the field itself, sampled according to this probability measure with times this constant, this square field, and now I'm going to look at their joint probability measure, and basically the result we got is a weak limit for this joint probability measure when you remove the cutoffs. To get a precise statement, I need this quantity called G star. Okay, here is the formula if you want. It's basically roughly of order epsilon. This is the coupling of the phi 4 at the infrared fixed point. And it's roughly epsilon because we're working near mean field where the non-trivial fixed point is close to the Gaussian fixed point. Okay, so here is the theorem that we got in 2013. There's lots of stuff, but basically we show that when we look at the joint distribution, then when we remove the cutoffs, it converges weakly to a well-defined distribution, a joint distribution for two random fields, phi and the square. They are scale invariant, so if you rescale, you get the same probability distribution. The measure is non-Gaussian, so this is the truncated 4-point function evaluated at the test function, which is just the indicator of ZP3. More importantly, the square field is non-trivial, so this is a normalization condition here. Here you see that the number that I introduced before, this multiplicative renormalization, hinges on what the Z2 parameter is, and it's not 1, which means that the square field has a different scaling dimension. This number here, this is the scaling dimension of the squared field. It's not equal to 2 times the scaling dimension of the field, as is true for Gaussian, for free fields. So this is highly non-trivial. Okay, maybe what does that mean if you, for a physicist? So if you look at mixed correlations, which we constructed rigorously, if you look at mixed correlations where you have the phi and you have the square, so phi square at different locations, y1, yn, if you rescale by multiplying here by L to the minus k, so if k is positive, this is like a positive power of p, so you're becoming smaller, and so you should blow up. So this actually, sorry, what am I saying? I hope I didn't get the signs wrong. Sorry, if I want to multiply, so if k is positive, this is a negative, sorry, if k is positive, this is a negative power of p, so this is bigger than x1, so I'm going towards infinity, and therefore the correlation decreases by this factor. But you see that there are 2 numbers here, which have to do with the number of phi fields, the number of squared fields. And so these 2 scaling dimensions are different. And in fact, we have a precise result, at least to order epsilon. We show that difference between these 2 quantities is about epsilon over 3. This actually was predicted by Wilson in '72. It's quite remarkable that this is a toy model for easing in 3 dimensions. If you put epsilon equal 1, that would be easing basically. And according to the best estimates using conformal bootstrap, these people here, this difference for easing in 3 dimensions over R, not over QP, is this 0.37, whereas what this suggests, which comes from a very, very simplified toy model, is 0.33. So it's not too bad for a non-trivial effect. All right, we in fact showed a bit more than this. So the previous theorem was about scale invariance with rescaling by L, which is a power of P. So it's a subgroup of the full available group of scale transformations. In fact, we upgraded this to full scale invariance. This is actually, you can find it in the thesis by A.J. Chandra from 2014. So when you look at the correlations of the fields without cutoff, so the 2-point function of phi looks like this. The 2-point function of the square field is similar, but with a different scaling dimension. Finally, note that a result, I mean, from this precise estimate of what the scaling dimension of the square field is, it tells you that if you look at twice the scaling dimension of the square field, so this is the power which appears here in the 2-point function of the square field, what is it? It's about 3 minus epsilon over 3. The key point is that it's less than 3. So less than 3, so that means that this power here is less than the dimension of space, and therefore this is locally integrable when x is close to y. And so here comes the next result. This is not an archive. What I proved is that, so these endpoint functions, mixed point functions, they are distributions, but what I showed is that these distributions are non-singular, I mean, they have a singular support, which is entirely supported on the diagonal where some points might coincide. So this is the result. So psi here is just a symbol for either phi or the square or phi squared. And so if you look at an arbitrary mixed correlation like this, it is given as a distribution. So if you integrate with test functions f1, fn, it is given by integrating this is an honest function of the points on the complement of the diagonal. And this integral is well defined. I mean, because even though this blows up when points become close to each other, the blow up is not too severe because of this condition here. So you're still locally integrable. It's a lucky situation. So this result, in fact, is related to this one here. So in fact, I obtained a very precise bound on the behavior of the pointwise correlation of the candidate for a CFT. When the points become close to each other, in fact, this is, if you look at points which are, say, in fact, you can remove this, but if you take points which are in a compact set, so they cannot go to infinity, but they can go towards each other, so you get things which blow up. How? Well, no worse than this. What does that mean? That means that for every point, zi, you look at who is the closest. So nn stands for nearest neighbor. So you take the distance to the closest other point, you raise it at the power, which is the scaling dimension of the ith field we're talking about, and you take the product. And so this is what I called a basic nearest neighbor factorized bound. And you can read about this in my recent article in CMP from last year. So this bound here, as well as the previous result of constructing pointwise correlations, this follows from a method which is the space-dependent renormalization group. And in fact, when you use this method, we get essentially an explicit representation for these CFT correlators, pointwise correlators, using things which look a lot like tree Witten diagrams. And so there seems to be a connection to AdS CFT correspondence. All right, how much more time do I have? Because I started at 11:04, I think. Hello?
You have about 10 minutes.
Okay. You mean including questions?
And it will be then 5 minutes for questions.
Okay. Thank you. All right, I'll try to give you an idea of the method. So this is the renormalization group for space-dependent couplings. Okay, if you've never seen what the renormalization group is, so here is the renormalization group in one slide. In fact, it wasn't invented by Wilson, it was invented by Landon and Gauss. All right, so this is the renormalization group philosophy, so to speak, because you can use it in many contexts in math. So the idea is, okay, suppose you want to understand something, let's call it Z of V. So it's a feature of some object, V. So how do you do that when it's too hard? Well, first you have to see the object as a particular element of a larger set of similar objects, E. And if you're lucky, maybe you can find a transformation from the set of objects to itself, which I will denote by RG, such that we have this exactly. What does that mean? That means the transformation preserves the feature that we are interested in. So if you can find such a transformation, then maybe if we're lucky, you can, starting from the object that we want, you can iterate the transformation infinitely many times. Maybe we converge to some fixed point, V star. And if we're lucky, Z, the feature at the V star, is actually easier to understand than directly from here. That's the basic idea. So here is a very elementary example. So these are elliptic integrals, of course. So here, an object is just a pair of real numbers AB. Okay, so E is just pairs of positive real numbers. Suppose we want to compute this. It's not in our calculus textbook. It's too hard. What do we do? There is a renormalization group transformation. So if you, this is the famous arithmetico-geometric method by Gauss, which is extremely fast in conversions, actually. Well, Gauss tells you just repeat. So take the original pair AB, compute this, the arithmetic and geometric means, and repeat. As you do that, you will actually converge to a fixed point where both of these are equal. And when A is equal to B, of course, this is trivial to compute. And this transformation, in fact, was found by Landon before. So that's the idea. Okay, now let's go back to our situation, which is a bit more complicated, but it's the same philosophy. So what we do is we look at, so we have this probability measure, which depends on the cutoffs. I want to understand the log moment generating function. So it's the logarithm of this ratio of well-defined integrals, where we see the couplings, which depend on the cutoff R over here for the phi4 and here for the phi squared. So the very first step is a change of variable, which is a rescaling to the unit lattice. So this is an exact thing, and it's very easy to do. This is because of the remark that I made that when you change the cutoff, the Gaussian measures are just scaled copies of each other. So I can rescale to make a change of variable. So the lattice of mesh L to the R becomes the lattice of mesh 1. So this is typical in Wilson's view of the renormalization group. So when you do this, the generating function, the log generating function of moments is the logarithm of a ratio of two integrals. So this is what I call the feature of interest, is the evaluation of an integral like that. So a Gaussian measure, a certain integrand, so I stands for integrand, R, that's we'll see in a second. So, it depends on F. So this is because I introduce a source term. Okay, so this is where the test function, the characteristic function, the test function appears. So the numerator is a certain integral with a test function F. The denominator is the same thing where F is set equal to 0. That's the partition function. But the integrand at the beginning is like this. So now G and mu are constants. So you can think of this as the critical Ising model on the lattice, and it's fixed. So there is no more dependence on R. The box has been made bigger. So this is a very big box because it involves the ratio between the ultraviolet and infrared scales. And if you look at the test function here, so this test function after the rescaling is a kind of diluted version of the original one. So it varies very, very slowly. And also it is, this number here is, this is a very small number because phi is about 3/4. So this is positive. R is negative. So the power here is basically negative going to minus infinity. So this big factor is small. So it's a dilution of the test function. Okay, so then, so the covariance C0 of the Gaussian measure, we're going to break it as a sum. C0 minus the next, so this is the covariance one level lower. So it turns out that this difference is positive in Fourier space. So that means that we can actually write our field phi on the unit lattice as a sum of two fields, zeta and psi. Psi is constant over boxes of size p. So this is kind of the coarse-grained field, whereas zeta is a fluctuation field. And if you want the formula in terms of the variables that I put on the tree before, that corresponds to basically only looking at the contributions between layer 0 up to the right before layer L. So finitely many layers. Okay, by using the property of decomposition of Gaussian fields, so this integral is the same as that one. And what I'm going to do is I'm going to integrate over the fluctuation field zeta. And when I do this, I will get an integral over psi, but psi, I can do a change of variable and rescale back to the unit lattice. So we write this integral over psi as a new integral over a field with the same measure d mu c0. What happened is that the integrand has changed. So from the original integrand, which was given explicitly by this, okay, at the very first step, when I do this integration, which means I perform this integral, so phi here is just a fixed field, I rescale it, I add the fluctuation field, I integrate the fluctuation field, and this was the old functional. Now I get a new functional of this phi, and so notice that here I change the index on the right to r plus 1. Okay, so here what we're going to do is we're going to iterate this. So also, there is a small modification, which means we extract a small constant each time we do this. All right, so there's a little modification here, but then there is an exact relation between the integral I had at the beginning and the new integral with the new integrand, and I collect this quantity here, which depends on the test function. And then I repeat the procedure. So then I'm going to get an integrand I r plus 2, etc. I'm going to do it all the way until this number here becomes s, which is the size of the box. So essentially the number of steps is the logarithmic difference between multiples of log big L is the difference between the small scale, the lattice scale, and the big box scale. And in fact, yes?
To the conclusion.
Okay, so so the way we prove our result is by controlling the sum of these quantities that we collect when we sum over all scales in the UV and ultraviolet. When we compare what we get from the numerator and the denominator, and in fact we show that this converges absolutely, and okay, there is a renormalization group calculation which we make in a rigorous way and allows us to do this. Maybe I should just simply fast forward to the end, and thank you all for your attention.